So here I'm going to present briefly the results of the first season that we've done on the Food Agility CRC project with Agric and Summerfood Australia. And this was the assessment of the accuracy of the handheld spectrometer that we developed. The basic idea of this spectrometer is that you've got a single system that can be taken in the orchard. So it's a battery operated system. It works off a smartphone or a tablet, and it can take a scan of a fruit at the tree without picking it. And with a single scan, you get a whole range of parameters that might be of interest. And so what it changes is essentially a calibration model that has happened in the background. So that's how the scanner look like. So this sort of shroud here is in reality is a dark cover that is flexible, so it can wrap around branches and so on, so you can reach the fruit to be scanned, and then the scan in real time get the parameters of interest on your smartphone. So the spectrometer briefly works in different modalities, and so these are acquired in the same scan. So just by pushing a button, then you'll get all these scans taken. The data is in real time uploaded to servers, and through the prediction models that are on the server, then the result is returned on a smartphone. What we did, the project with the Food Agility this year, the past season, was about developing models for firmness and sugars and Brix, and try to also determine the occurrence of storage disorders in fruit. So there's two different experiments I'm going to talk about now. Okay, so the first one was done with Intaktura, and so that's there were 5 cultivars that were chosen for the experiment, and in all cases the fruit were scanned with Rubens, and then the destructive testing was done on the fruit, and so the conventional measurement of sugar firmness and eventually other parameters like the DA meter, the ethylene was also collected, and dry matter, and I believe all the other things like size and so on. So then after this was done, we developed machine learning models that takes essentially the spectra that Rubens acquires and trying to predict the value that the destructive testing was given. And so then we can, with that information, we can evaluate what is the accuracy. So for instance, here is an example done on, this is Snowflame 25, that's a white peach. So here in these graphs on the x-axis, you have the measured quantity done by the destructive testing, and on the y-axis you have what is predicted by the spectrometer. So you would like to have those data sitting nicely on the 45-degree lines. So that's then there is some scattering around that, and that's enables us to evaluate what is the accuracy. And so here we have within 5 to 10% values the error of the primary data. So, and then in this case we did model for all of those things. And here I see, for instance, the Brix, the firmness, and the ethylene. This was done on an average of 300 scans per cultivar. In this case here, the graphs were shown, the data were taken, the scans were done in the lab, but we also tested the scans done in the orchard. So for instance, here there was this September sun. These scans here, about 90 scans, were taken all in the field with Rubens, and then the fruit was picked and the destructive testing was done after that. And we do not see any decrease in accuracy because of that, and so we wanted to test these things, and to have a good test of working with the scanner in the orchard, and that was important. And the other experiment that was done was to use the scanner, the Rubens scan, to try and predict the occurrence of storage disorders. So this was a bit more complicated. So there was a number of fruits, and the scan was done at harvest. Then the fruits were put in cold storage for a variable number of weeks. And they were also then taken out of cold storage and left at room temperature for a variable number of days to simulate retail. And what we try to do is use the scan. In all those steps, the fruit was scanned as well. And at the end, they were visually assessed for any types of internal disorders like browning, mealiness, rubberiness also. So what we found is that if we scan a fruit, we have more than 90% accuracy. We can predict if that fruit at that moment will have a storage disorder. So if we, for instance, there is browning in there. Now, if we, instead of scanning at that moment, we use the scan that were taken earlier when the fruit was first taken out of cold storage, so we have still more than 80% accuracy in the occurrence of internal disorders in a few days. So by the time that the fruits, let's say 2 or 3 days after removal of cold storage. And then we did the same with the scan at harvest. So what happens? So in that case, we can use the scan at the moment in which the fruit is harvested to predict the likelihood of this fruit displaying some internal disorder in a few weeks' time. So after being through cold storage and eventually retail time. And so this was obviously, it's done only on a single cultivar. This was on the yellow, the O'Hare yellow peaches. So it probably needs a little bit more validation, but this data is very promising for what essentially trying to use the scanner to have a prediction in the future of the likelihood of all the quality of this fruit. Now, the last things I want to say is that we all these models were done on individual cultivars, but in some cases it might be easier to actually deal just with generic models. For instance, here is a yellow nectarine or white peach or something like that, rather than having individual cultivar models. So in this case, there was some data from different types of different cultivars of yellow nectarine here listed here, and they were taken from different orchards. And in different places. In this case was Cobram Shepparton, and so we can also generate models that are generic in the sense that, as you can see, there's bricks and firmness for a yellow nectarine model. That's about it. I would like, if I have a few more minutes, actually just show a demo of how the system can work. I will share my screen where I have, I have here, is that visible? There is the screen of my tablet in there, and I have with me the prototype spectrometer. That's, I mean, it's probably visible in the small camera image. So I have connected the scanner to my tablet, where there is the app in there that is visible. So that's connected to that device, and then I'll go on a scan tab. In this case, I haven't got stone fruit. I've got an apple here, so I'll select the apple Granny Smith over here, and I can start the scan. The app asked me to put some label in there. So for instance, I have, we can say it's a block 1 or something like that, a label. And then we scan the apple. That if you can see on my camera, that's how the apple's in the device. And then so get the scan in there. Now it's being scanned. And it takes a few minutes. Now the data is being transferred from the device via Bluetooth through the app. And through the server. Now the model is analyzing this data and returning a value for that is probably a bit small, but it's written there firmness and bricks value. In this case, these are where the models that are available for this particular fruit. But then you can, if you have more models, say for instance you need ethylene, or you need a diameter, or you need a color, or whatnot, that can be just listed in there in one single scan. So that's the idea. So one can repeat the measurement a few times and get a few stats on the same on a block, for instance. And this can be a quick way to estimate the quality of the fruit. And this data is also available on a dashboard, so that you have all the spreadsheet of scans that have been taken and the values of firmness and Brix for the various fruits. So that can be easy to export, for instance, in Excel or something like that.